In this video, we're going to talk about how you can determine the maximum shear stress for a 3D state of stress and the plane that maximum shear stress acts upon. So for the 2D, so we talked about in the last few videos about how the maximum uh, shear stress in 2 dimensions on a 2D Moore circle element is a 45-degree rotation in the clockwise direction from the first principal strain direction. Okay. This is not always going to be the correct maximum shear stress and plane orientation for during 3D stress cases. So in 3D stress cases, we know that the maximum shear stress, we defined it using 3D Moore circle as being the first principal stress minus the third principal stress over 2. So please always use this equation when you're trying to determine the magnitude of the maximum shear stress. All right, please use that equation only. All right. So when you're trying to determine the second step of this is you have to try to determine the planes containing the maximum shear stresses from the original coordinate system. So if you're given a coordinate system stress state in 3 dimensions in the XYZ coordinate system, you can determine the principal stresses using the determinant of the original stress matrix minus the principal stresses times the identity matrix. And if you set that equal to 0, you can solve it. And you end up getting a cubic root equation, which you can solve for our 3 principal stresses, sigma p1, sigma p2, and sigma p3. All right, using sigma p1, sigma p2, and sigma p3, you can plug them back in to the original equation here and multiply them by our eigenvalue and set it equal to 0. Okay, so if you do that, so you can also solve this problem using MATLAB, all right, to get your eigenvalues or your principal stresses and your directional cosines. So the only thing you have to be aware of in MATLAB is if you do have your directional cosines, you do have to transpose this matrix here to get the proper transformation matrix here that you can use to go from the 2D state of from the original XYZ coordinate system to the first principal stress axis, the second principal stress axis, and third principal stress axis coordinate system. Okay, so after you do that rotation, you end up getting this equation to determine your principal stress matrix. Okay, from the original XYZ coordinate system matrix. Okay, so the next step is that you'd have on this problem is you need to get to the plane of maximum shear stress is we know that the maximum shear stress will occur if you rotate 45 degrees about the second principal axis, which is like the middle, the in-between of the two, the maximum principal stress, which is sigma p1, and the minimum principal stress, which is sigma p2. All right, so to do this rotation, what we need to do is we need to take the we need to find the projections of the 1' axis onto from the one axis and the principal and we also need to determine the I apologize. I drew this arrow in the wrong direction. It should be going along this direction here. All right. So to determine the projection from along the one axis on the 1' axis, we need to say that would be equal to the cosine of this vector. So the cosine of 45 degrees. All right. The projection of 2 onto the 1' axis is going to be equal to the cosine of 90 degrees. All right, and then the projection of the vector 3 onto the 1' axis is going to be equal to the sine of theta. All right, or it's actually going to be equal to the negative sine of theta, since this vector here is going along is going opposite of 1'. Okay, so we can repeat this process for the projection of 1, 2, and 3 on the 2' axis. So we would, in this case, we would get cosine of 90 degrees, we would get cosine of 0 degrees, and we would get the cosine of 90 degrees. All right, and then if we repeat this process for the projections onto the third axis from vectors 1, 2, and 3, we'd end up getting the sine of 45 degrees for the first row, first column. For the second column, we would get, again, cosine of 90 degrees. And in the last column, we end up getting the cosine of 45, the cosine of 45 degrees. Okay? All right. So if we plug in this transformation matrix into this rotation, we can call this matrix T rotation, and we can say that we multiply the rotation matrix times our principal stress matrix times the rotational matrix to the transform, we would get our stress matrix for the maximum shear stress. Okay, so our maximum shear stress will be within that stress matrix, and then if we substitute in for our principal stress into this equation here, we end up getting the following equation where we can directly solve for our maximum shear stress. So and then our if we multiply our maximum shear stress our rotational matrix times our principal stress transformation matrix, will get the transformation matrix for our maximum shear stress. So what that ends up giving us is it'll give us a matrix of directional cosines relating that will give us a transformation from our original XYZ coordinate system to the 1', 2', and 3' coordinate system where our maximum shear stress is at. So after we do this, I'm just going to define these two matrices, and that will be the end of the video. So after calculating the tau MSS using the rotational matrix and the principal stress transformation matrices, you'll then end up getting a shear matrix with 6 components. Your three stresses along the 1', 2', and 3' coordinate system, and your 3 shear stresses tau 1, 2', tau 1, 3', and tau 2, 3'. One of either tau 1, 2', tau 1, 3', and tau 2, 3' will be your maximum shear stress.